So thanks to the organizers for this very nice conference and for the opportunity to speak here. So I think I'm the only talk that I'm giving the only talk that has something related to machine learning. So I will try to be a little bit introductory with some motivation for the machine learning and things. So also I wanted to thank, okay. So before of the organizers, so these two groups of people, I mean the last ones, we started discussing these subjects of machine learning, tensor networks and stuff in a nice program in the Newton Institute. And I'm very much thankful to the group of Johanna in Würzburg because then some of this exploration so started to get concrete. Okay, so I will start with a summary, motivation, so talk about many things that I'm calling emergence of space-time from neural networks, and then describe the Ising model, present the conclusions and further directions. So, so this is a summary that is, of course, something similar to that is already on the web page. What we do is to explore tensor networks, in particular random tensor networks, and we are following a known prescription so that establish that these random tensor networks can be related to two-dimensional Ising models on the bulk, so by making a time slice. And so more concretely, so you can compute the entanglement entropy of these random tensor networks in terms of a free energy difference in the Ising model. Well, so the Ryu-Takayanagi formula is working here, and the machine learning algorithm basically, so is what it's doing is to update the couplings of the Ising model. So we will get to that. So what we do in this part of the work that so is to study the dual CFTs to ADS3 and the Bizet black hole. Okay, so many talks in this conference last week and this week. So the one yesterday of Veronica Hueni and the one last week of Bartek and many others. So explore the minimal surfaces as a measure of entanglement. And it's already like 19 years of this, so that these discussions started. So entanglement, most of the people in the audience are convinced that it plays an important role in the ADS-CFT correspondence. So in general, in the correspondence between gravity and field theory. So we will also employ that. So on the other hand, I think also in some of the talks, there were some elements of tensor networks. And they were first studied in the condensed matter theory community to study the renormalization group flow. So one has like some microscopic degrees of freedom. So when the scale is running, so you can have like effective degrees of freedom describing the same system. So there are, of course, many more works, but I'm citing here these works of Vidal and Swingle that started the thing. Okay, so now, before I get into this slide, let me tell you something. So why we started this project? So in a way, so I got to know machine learning as a technique for string phenomenology, for the exploration of the landscape. And on the other hand, these ideas of space emergence from entanglement, so I was finding them always like very interesting. And of course, they connect to the tensor networks, no? But the tensor network, so they are also like hints that you can connect them so with learning and with machine learning algorithms. So searching, so what was done in this direction, this connection of random tensor networks with the Ising model so this was something that is something concrete that one can realize. But okay, so now I come to my slide. So this list is just few of the works, but one important reference is this review of Fabian Rühle. But so people in the last decade, let's say already, have been exploring machine learning techniques. So for various problems in string theory. Okay, so for Calabi-Yau metric, so to find, let's say, good approximations to the Calabi-Yau metrics, to study cohomology, to explore for vacuum statistics, and of course, also to make more analytic approaches. So the machine learning models sometimes can also like generate hypotheses, and they can be tested towards analytic formulas. And in the other hand, so there is a flow. So there is a flow also in the other direction. Like so, people have been also working in improving the current machine learning techniques, like using techniques from theoretical physics and mathematics. And yeah, so well, in particular, I cite these two works that they are recent on this direction. Okay, and of course, so people also have studied some of these neural networks or more complex networks in analogy to physical systems and in analogy to quantum field theory. And I think this is an important work on that subject, but there are many much more. And okay, so there are many applications. For example, in the study of knot theory, more so recently in the study of integrable systems, and many things, more than one can say. But okay, so what is more relevant to what we are doing, I mean what connects more to what we are doing, is machine learning in the context of the ADS-CFT correspondence and gravity. And there are these works started by Hashimoto, so where they study the bulk. I mean, you have the ADS-CFT, you have the CFT in the boundary, and the gravity in the bulk. And so they study the bulk as a neural network, okay? So in every layer, so the layers of the network would be the radial parameter. And in this work, by providing boundary information, so they can reconstruct what's going on the interior, okay? And so for giving a feeling to you of that, I will have a slide of what the neural network is, okay? So also, you can do it in terms of other networks, that they are deep Boltzmann machines. And this last sentence here is important because, well, so we recently found that people have also studied Renyi entropies, so like multiple intervals Renyi entropies with the use of neural networks, which is somehow analogous to what we are doing. I say in spirit it's the same, but it's different because in our case, so this network is supposed to, to give you what's the optimal tensor network to explore, okay? So, okay. So if you have any comment or question, they are welcome. Okay, so I will give you a flair of what machine learning is, but maybe many of you already shaked a little bit of that, even if you are still not using it for your work. So the standard artificial neural networks, you have n layers. So as I was telling you, that for example, in these works, that reconstruct the bulk from the boundary. So the layers would be the radial distance. So the layers are, so it's the number of layers. So you will have L denoting each neuron. And each neuron at layer L is connected with all other neurons in the next layer. And you have something that is called the weight factor. So the relation that you have is that the response of the network, okay, let's say the neuron at the next level is connected to the neurons in the previous level okay? And you have these constants W, B, I mean, these terms, W and B. And what you are doing in every run is to optimize these constants. Okay, so K goes through the number of layers, and what this is called the bias factor. This is just a technical way of calling it. But okay, AG0 represents the input data, and AGN represents the output data. So I have a picture for that there that is colorful, that that you can see it well. I mean, the yellow is the input, and magenta is the output. And so this is like the structure of the simplest, let's say, neural network. So many of the algorithms that come later, they inherit from there. And basically, so what you are doing is that you have also something that is called an activation function, and you define the cost function. Okay, the cost function is what defines really your problem, your information, so in this case, physical information. So for us, it's a different architecture. It's something different to that I will present you later. But the cost function would be, in our case, the difference between the entanglement entropy of the real system, I mean analytically computed, and the outcome that this network is giving. Okay, so I go into the figure, and yeah, so you call it deep learning when there are many layers. Okay, and this is the deep learning meaning. Okay, so I have another drawing here, and this is tell me how many. I would say more than 2. I don't know. Okay. Yeah, I mean I have seen it call it more than 2. So in the work we did for stream back and so on, we only had 3 layers. Well, we didn't call it deep learning, maybe 4 or 5. So it's yes.
And many, because it's linear relation between the input and output, right?
This is the thing, the relation is not linear. If it would be linear, then it's just like a matrices multiplication. I don't know if this is what you are saying, but let me go here. Let me go back. So this is very non-linear. So this is the, I mean, this is like it's like a step function that is smooth.
So is the a minus 1 there?
Yeah, no, the sigma. So it's 1 divided by 1 plus the exponential. So it's like a step. It's like a step function. So and this, I think this nonlinear thing is what really makes a difference, because from one layer to the other, you have like a very nonlinear thing. And when you are updating the weights, I mean, this basically does that some of the weights will go to 0 and some others will become very heavy and so on. So it's this, yeah, okay, here is the linear multiplication, but then you evaluate all this argument in sigma. So this is something that, and this, I mean, well, this is a particular choice, but people, I don't know, so you can use a step function, something that is linearly, but the point is that it's a step kind of thing. Yeah.
The minus 1 is a typo there. Ah, the previous step.
Sorry, which minus 1?
Minus 1 in the A prime, this one.
Ah, no, it's L. Here, you say?
Yeah.
Oh, no, it's L minus 1. So it's the previous layer.
Okay, yeah.
Okay.
Yeah, I just wanted to understand, like, how, like, the activation function, how you get this activation function. You said it's a choice, like, is there any motivation?
Okay. I mean, I'm not a machine learning theorist, but I can tell you that these people, when started trying with these things, they tried this one and it's good. But the importance, I think, is related to the question that Horacio Cassini did. I mean, so the thing is that this is non-linear, but you can have something that is also a line in the middle. Yeah. So you can use many activation functions. And I think the people that work theoretically in that, they have proven some theorems that if this converges and so on for various activation functions. But this is a choice.
Relation between x and y?
the X and Y. Okay, no, this is a terrible typo. I'm sorry. I'm sorry. This is X. So I searched for typos, but that one I couldn't spot. Sorry. Okay. Thank you for the questions. Okay. Basically, so let's say this is the simplest thing. And okay. So now, so I'm following a prescription that they started. It's now like 7 years ago. So where basically, so you now, of course, treat this Ising model as the network. And this was done, so I think before, but for other cases, because Ising models, they are called also like Boltzmann machines. I mean, people also explore it, but in different contexts. But now you will have a hyperbolic network, okay? And so this is a two-dimensional Ising model. And in their case, they apply it to a theory in the boundary that it would be a 1D Majorana spin chain, okay? And so this connection has its origin in this mapping that random tensor networks you can write in terms of this Ising model. I will go to that soon. And what we are doing is to write a cost function that will be telling you how different the entanglement pattern of the CFT you want to approximate is from the entanglement from the free energy difference in the Ising model, but we are coming to that. Let me see. Okay, good. So, yeah.
So why is it the second Rayleigh entropy? Because it's the easiest thing to compute, or?
No. I mean, in the paper, the Rayleigh entropy also you can map to another, to different Ising models. So so we took the second to start with, but I think each Rayleigh entropy you can map to the different Ising. Thank you. So okay, so then I will go a little bit further and then back. Okay, so this is a drawing of the tensor network, and then you have the vertices and you have the edges, okay? And then you have random states in these vertices, and you have entangled pairs in these edges. But now I'm coming back and I will write the formulas. Okay, so a random state that belongs to this Hilbert space at vertex V. So this Hilbert space is divided among all the edges that they go to that vertex. And so you define this random state by superposing, I mean, by summing using random tensors that they usually, so they are taken from normal distributions. And so this mu VE, I mean, again, V is vertex and E is edge. So it's a complete set. And also, so this information is what is encoded, I mean, drawn in the tensor network drawing. So the entangled pair state, you can also compose by summing, so over the different vertices that they go to an edge. And in this tensor network, so this allows you to compute the mutual information. That here we are still, so we will, I'm not using it yet, but this is some information that you can gain from that. And okay, so I have a little bit more of explanation here. I mean, so the random tensor network state is going to be given by this set, okay? So vertices, edges, and mutual information. V denotes the sets of vertices, E the set of edges, and I the mutual information of the edges. And here I'm going to say something. I mean, so this maps to something that is proportional to the couplings of this Ising model, okay? So this mutual information on the edges. So you can define, I mean, so this is the state, and you can project the entangled pairs. And the physical Hilbert space is going to be formed by the external vertices, okay? Because here you are tracing over this information. So now, if you have this random tensor network state, so you can make an average over the randomness. And if you consider a subregion of the boundary, so the second Renyi entropy, you define it as so with the trace of the reduced density matrix square, okay, divided by the normalization. And so this is an average over random states. So in their work, so Hayden, Samiki, Thomas, and Walter, so they show that you can write this particular entropy in terms of the free energy of this Ising model. Okay, the Ising model is, as we know it, the Ising model we know. Okay, there are couplings, and so spins, they are couplings. So this would be like all the vertices. So this would be the two vertices that belong to the boundaries of one edge. And so this is an external magnetic field. And the couplings that we are going to train, they are related to I, okay? So this JA, they are related to I. So, okay, I have another drawing, like to summarize this thing. I mean, the prescription of this translation, so once you understand it, is relatively simple. So the spins that they are, so that they belong to the subregion, okay, they have one orientation, and the spins that belong to the complement, they have the other orientation, okay? And so you can like count, okay? So it's this thing, so it's discrete, that so we are treating, of course, it's discrete the way we are treating it. You count the numbers of spins divided by the total number, and this is like the L, so the interval to the total size of the system relation. And okay, so they established this correspondence precisely in the limit when this information is very big. And so this is what I just described in the previous picture, -1 when, so when the spin belongs to the region A, 1 when it belongs to the complement. And this T0 denotes the case when the complement is the whole boundary, okay? So when you have all the spins in one direction. And what we denote the entanglement feature is the set of all entanglement entropies. Of course, yeah, compared with Veronica Juveni talk, so we don't have so many, we don't have so many elements of the entanglement feature, but it would be desirable. I mean, so far in this work, we only did like 1 or 2 intervals. Okay, let me go again. So what we are doing is to optimize the graph geometry, and the training set is this, this equation, 6 here. I mean, so these are sets of spins that they have one or the opposite orientation, and these are the sets of entanglement entropies. So this would be the input we are giving. Yes?
Up and down in the two regions. What is the meaning of that? I don't understand that. What is
what's the meaning on so the?
You are putting the entropies of the Ising model as a data, something like that, right?
No. So what I have a CFT2 on the boundary,
yeah,
and then so I want to search for the tensor network that reproduces me this entanglement entropy in the boundary.
Yeah.
And the way this is done, that this was what they show, is that you can treat this as it's like a domain wall. I mean, like, so that you can compute this by subtracting the free energy of this configuration when you have this change of spins up and down, and the free energy of the system when everything is aligned. So this is
so the data is this free energy, the free energy of this configuration.
No. My data is going to be the entanglement entropy on the boundary theory. And this free energy is the tensor network information. So it's what the tensor network is, how the tensor network is approximating the entanglement entropy. So the Ising model is in the bulk, okay, and it's a representation of the random tensor network. And in the boundary, what you have is the CFT too. And then updating. So updating the couplings of the Ising model is updating this mutual information of the nodes of the tensor network. All of this in the bulk.
Okay.
I did it a little bit more clear. So I think, I don't know. So I think maybe it gets a little bit more clear, but let's see. But yeah, I mean, this is okay, so it's a resource, let's say. So this Ising model is a resource to compute that. Okay, so this is let me look at the time. Okay, I have 15 minutes. So, okay, so we have this data, and then the cost function is going to be, okay, maybe here. So this Sj is, so it's really the entanglement entropy I'm getting from the tensor network, and S5 is the model, I mean, would be the 2D CFT entanglement entropy. So, and so we are doing is updating in each step this cost function, okay, to find the optimal coupling or the optimal mutual information. So I took borrowed from them these two figures, and basically what we are doing is that in every step you update mutual information or couplings using this cost function, okay? And then, well, in this paper they consider cylindrical or hyperbolic network, and I think, of course, so hyperbolic network had better results. So this is, again, I'm borrowing the plots from them. So hyperbolic network has much more better results because this model that they consider, it has a conformal point. And yeah, so because ADS-CFT duality, I think this network reflects more the bulk. But the question is that, no? So given the entanglement feature, I mean, given a set of entanglement entropies, so one can, how one can determine the optimal geometry, okay? And now, so we want to apply this, but to different CFTs geometries. And what we started doing now, so is the case of ADS3 gravity dual, and the case of the BTZ black hole dual. This is a way of discretizing the space-time. So these subregions of the boundary, so these are like the domain walls of the Ising model. Okay, so comments, question, or I continue? So, well, this plot I did here is just to give you a flare of what this is working in terms of learning. So the green, I hope you can see them. So the green nodes, so these are the spins, and this is a very short network, okay? Here I have, so 4 spin, again, the hyperbolic structure, so 2 in this interior, and like that. And so what we do, so is to use, so these results that show that you can write for this Ising model, you can write the partition function in terms of this dual network. So the magenta is the dual network, and so computationally we have to construct this for many cases. But basically it goes like this. So the information of the partition function this is the icing model now on the bulk. So you can cast it in this dual network by computing the determinant of a matrix. That the matrix of this dual network will have values. The elements will have values 0, -1, e to the 2j, minus e to the 2j. And this value of the elements, it depends. I mean, if there is no connection, the element is 0. If there are these small triangles, so the element, so the connections are 1 or -1, independence of the orientation. And if you have a line that crosses one of the original couplings, then the connection is e to the 2j. I mean, these are old results, but very useful here. And okay, so this is what what I just summarized before. So the original couplings of that network, they are JA. The dual edges will have weight e to the 2ji. And so these tripartite vertices that you introduce, so I mean, these are just like, operations you perform on this partition function, and you can compute that. So they have values 1 or -1. So the lower spins are connected to an external magnetic field, and this is determined by the connection with the tensor network. So you have to start from the external point and assign a float to the lines, and the ambiguities you just have to correct, okay? So this is the example that we gave here, but we are going to, okay, so we are going to make this network bigger, okay? So, well, now I go to machine learning again. So what we are doing, so people that are using these techniques now, so you can use, for example, things that they are already done in Python. In particular, so the group in Würzburg had a nice program that already had these things implemented. And what we use is this Adam optimization. Okay, so there are momentums and there is root mean square propagation. So basically you have these two variables, this mt, vt, that they are updated at every iteration. But what is more relevant, I think, is this slide. So this is the cost function, jt, and we compute the gradient of the cost function. And so we compute these two variances at every step. And basically what this thing is doing is that in each step we update the couplings, and the rate at which this coupling is updated depends of how much is varying. These two momenta are varying. Okay, so here I have a line of code for you to see that that this part is not so complicated to implement, because already many people develop packages for these things. And so you call the Adam optimizer, you put your cost function and your momentum, and then so you can continue. So okay, so first thing, ADS3, I have to hurry a little bit. So ADS3 gravity, and so if we write so here I don't have the reference, but if you write the entropy for a single interval, and you make the identifications of the cutoff in the gravity and on the CFT side, you get the Ryu-Takayanagi formula. And so what we do here is I'm showing you some of the plots, okay? So now, so this is a CFT with cyclic dimension, okay, 2D. And so this is an example taking some data points, some central charge, some cutoff, and some learning rate. And okay, so this is how the loss function is evolving. And this blue, I'm sorry, the letters are small, I didn't correct them. So the blue is the entropy, and the orange is what the network is giving you. And I would say, okay, so this is still a single size thing. So, but now we can, okay, let me make a point here. So we are matching the entropy of the random tensor network and the CFT. And of course, these things are numerical, no? So you have to explore data size, number of iterations, network size. So far, this is just 64 nodes in the outside thing. And okay, so now if we consider another geometry, so the Bizet black hole, do it to determine CFT, and you have here this other, so the formula that matches the entropy to the length. So we also perform the same exploration, and so we consider, so this is for these 30 data points, some central charge should violet cutoff, but you can do this for different central charges. And okay, so we find so far convergence that is 10 to the minus 2. So the example in the original paper, they had already better convergence, but we are getting there, so it's just a little bit more time. I mean, more time of computing. Okay, so I'm sorry. So this plot looks a little bit ugly, but I explain it to you in the following. Okay, so one interval is not enough because this is just like fitting one curve, no? And it doesn't have the whole information of the entanglement features of the problem. So next what we did was two disjoint intervals. And two disjoint intervals, so you have, if you have a boson, CFT, so there are some Jacobi functions. If you have n intervals, there will be some C of Weil, I think, theta functions. But okay, so in this optimization, so now we take 1 and 2 intervals, and we trade the network with 1 and 2 intervals, and also we have reached so far like 10 to the minus 2. These things that looks like an electrocardiogram is not so bad, believe me. I mean, so if you look blue and orange, I mean, basically the blue, so the thing is that I define here length as the sum of the size of the intervals, which is probably not the better variable. But so if you have the blue, so this would be the entanglement entropy, and the orange is what the network is predicting. And yeah, so they are matching in cost function up to 10 to the minus 2. So, okay, I think I'm almost finishing. So it was an exploration of tensor networks employing this correspondence with the Ising model. I mean, so far, so we just we explore the CFTs dual to ADS3 and Bizet, and the precision is 10 to the minus 2. So we are exploring, so we explore cases 1 and 2 with the same precision. Of course, so this is another bit in this whole quest of understanding the space-time as the realization of microscopic degrees of freedom. And what this has been explored in the last 2 decades a lot, and this conference is a sample of that. So I want to say, to finish, that of course we have to complete this with for the multi-interval case. And so we can also use some recent results to determine if the setup is trainable or not. And this is something that yeah, we want to do next. And I would say, yeah, the experts please can comment or tell me that in this bulk description from tensor networks, still the dynamics is a problem, no? And so it would be something good to go there. So I thank you all. And yeah, I have a thank you.
Okay, we have time for questions.
So how can you see, for example, features of geometrical features in your network? So how does the network encode geometrical features?
What? Geometrical.
So you train your network and then it should somehow describe a geometry. So can you, is there like probable?
Okay, I mean, so the geometry is a little bit encoded already in the hyperbolic structure of the random tensor network, no? So, but yeah, so the distances are encoded in this hyperbolic structure. But I would say, I mean, so far what I did is like, so to consider a lot of symmetry on these couplings, no? So this is like very symmetric. It has, but if you want to explore more interesting geometries, so I think you have to relax this. And so the different couplings that would be different mutual information, I think these things can say something about the network. But so far for these two cases, it's just like simple, I would say. Thanks.
Hi, thanks for the nice talk. Your last slide confused me a bit. So you claim to do holography, but then
which one?
There's the free boson, essentially, which is free. It's not strongly interacting. It's not large central charge.
Okay. So
I kind of miss the, like, where would holography really enter?
Okay. In the last slide is CFT2. I would say, because also it's not like large central charge, because it's one boson, no? But so I wanted, so of course there is this universal part, no? There is some universal part to the n interval formula, but this is a little bit too model dependent, no? So I took it, yeah, so as a CFT2 model. I mean, I would say if the central charge is so small, maybe it's a little bit far from holography, but if I would have something for higher central charge, maybe this would be just the geometry, I think. Mm-hmm. Johanna has a comment or a question.
Okay, just a quick comment. I mean, of course, we're not doing holography here. I mean, we just say we want to train a network that realizes this particular Venn entropy of the boundary theory. And so we just update the couplings to such that the network reproduces the initial data. But I mean, from there, I mean, as Nana was explaining, we don't yet have a geometrical explanation of what a boundary. I mean, you can just choose any initial data and then just use this network and see how the network finds this result. But I mean, from there to actually say something about holography, this is a big step. I mean, it's interesting that you can do it even for small central charge, but I mean, of course, we don't have the dynamics of the theory in the bulk. I mean, this is not done here yet. Okay.
It's a little bit far yet, but yeah.
If you imagine that there's pieces of the bulk that are somehow correlated in the bulk, and your edges are counting the mutual information, I would have presumed that little bit further away pieces of the bulk would also be correlated, and therefore your network would not be a planar graph, but something highly non-planar. So that's just a comment or question whether you have thought about that.
Okay, yeah, no, I think it's interesting. I mean, so now, something happened here, wait. Yeah, now in a way, so they are, so far regions, of course, they are, I just wanted to go to a hyperbolic thing. So they are less and less connected, but you would say, okay, so you should introduce a mutual information between nodes that they are far. This sounds interesting, but yeah, so I haven't thought so far about it. But I think, well, I don't know. So I think people explore other networks, like the computer scientists and so on. They are like multidimensional. Maybe one can think about something like that. But in this context, so I cannot say anything more. So I think it's interesting because it's true. So you could correlate them, but of course, I think as there is entanglement between all these different vertices, so you can probably compute also a non-zero correlation between some nodes that they are not neighbors. Maybe there is also a non-zero correlation between nodes that they are not neighbors.
I don't understand what your links mean.
Okay, let me see.
The only things that describe the correlation and what you have sort of doesn't look like a space-time to me.
No. Okay. Well, I meant in the random tensor network. In the IC model, yeah. So a representation, I think you are right. So you need some couplings connecting things that they are not neighbor. It's true.
Okay, let's just take one more question and maybe save the rest for lunch break.
You said that you got down that you got a loss function down to 10 to the minus 2. What are the time scales involved to get to such?
Well, in my
10 to the
computer.
minus 2. Are we talking about minutes, days, hours?
Yeah, in my computer, it's just the break, just like half an hour, like
Half
that.
an hour.
But I'm not using like very big resources for that so far.
Okay, let's thank Nana again.
Thank you.